In the first example, we were passing a copy of the value itself. We're using value semantics. In this example, we're taking its address and passing the address up. We're using pointer semantics. Now, you might think that what we have after this call is something like this, where main now has a pointer to a value that is on a stack frame below. If this was actually the case, we would be in a lot of trouble. Because I told you, once we come back up the call stack, this memory, it's there, but it's reusable again. It's no longer valid. Anytime now main makes a function call, we need to allocate the frame and initialize it. I want you to think about zero value for a second. What's so brilliant about zero value is it allows us to initialize every stack frame that we take. Stacks are really beautiful data structures because they're self-cleaning. We clean our stack on the way down. Every time we make a function call, zero value, initialization, we're cleaning those stack frames. We leave that memory on the way up because we don't know if we need that again. It would be really inefficient to clean those stacks. But every time we make a function call, we clean, we clean, we clean. So if we look at this scenario, this would be bad. It looks like we took the address of this user value, we passed it back up to the call stack above us, we're now done, and it looks like we have a pointer to something that is about to get erased. This wouldn't do. I told you in the very beginning, in the first video, Go has this amazing balance between readability and simplicity. And what is readability again? It's about not hiding the cost of something. And what is simplicity? It's about hiding complexity. And so what's brilliant here is Go is going to have this balance. Because what's going to happen is based on the convention of our code, the compiler is going to perform escape analysis and make a decision on whether the values that we are creating get to stay on the stack. We want to leverage the stack as much as possible. It's going to give us some mechanical sympathies. It also gives us some better performance because the stacks are self-cleaning. But remember that sharing can also add levels of efficiency. But when things need to be shared, they can't stay on our stack. So when we look at this thing, when we look on line 39, anytime we take the address of something like this and we're now passing it up, we're sharing it up the call stack. So this won't work. So what's going to actually happen? Well, escape analysis is going to do the following. It's going to say, okay, here's main. Here is our function here, escape to heap. Escape to heap, here it is. But because of line 39, this value of user cannot be placed inside the stack frame for this function. We're going to have to put it out on the heap. It's going to have to exist not on any stack, but out there in what I would call the whiteboard. What I normally like to do is say the following. Hopefully you have a notebook in front of you. If I was in a classroom, most students would have a notebook. Think of that notebook as your personal stack. That is a place where you write private notes, and every page being a stack frame, right, that has that boundary. But if you needed to share a note with somebody next to you, you couldn't give them your notebook. You can't rip that page out. What you have to do is go ahead and write those notes on the whiteboard so everybody can access them and everybody can share them. And that's what escape analysis is trying to determine. Does this value get to stay on the stack in that stack frame in your notebook? Or does it have to be placed on the whiteboard for everyone to be able to access and share? On this first piece of code here, because we're passing a copy of the value itself, it is safe to keep these things on the stack. But once we share something up the call stack like this, escape analysis says this memory is no longer going to be valid. When we get back up here, we must put it out there in the heap. And what's going to happen is main is going to end up with a pointer here. In fact, this allocation happens immediately on the heap. In fact, escape to heap is going to have a pointer. But U is going to be based on value semantics. And step back and think about how beautiful this is. Inside this function, we get to leverage value mechanics, which are simpler to use. From our perspective, this is a value of type user, and we operate against it as a value. But underneath the covers, because of escape analysis, we really know there's a pointer, because there can be nothing on the heap without some sort of pointer access to it from some stack or global space. And this is what we have. We have what we call an allocation in Go. And when we have an allocation, that is when the garbage collector has to come in. The performance of your software is going to come from a couple of places. One place is going to be, as we're going to learn, how we lay memory out and how we access memory. Another place is going to be algorithm efficiency. If we can do things in less instructions, let's do it. And another place is going to be by reducing the amount of pressure we put on the heap and therefore the garbage collector. And so we want to leverage the heap when it's important. There's efficiencies there. The garbage collector will not get in our way. We have to share things. At the same time, if there's a value that doesn't need to be on the heap, if we can leverage our value semantics and keep it on the stack, we can be better for it. There has to be a balance between value semantics and pointer semantics. This is what we're going to be learning as we move forward. In this case, we're now using pointer semantics. More importantly, this user value based on the variable U is actually in the heap. Here it is. It's being shared from this stack frame. It's now going to be shared from this stack frame as we share it up. And another thing that really gets me sad quite a bit. You may see code like this written in Go, and you may see a lot of developers do this. What this syntax says is create a value of type user, take its address immediately, and turn U into a pointer. For me, this is really clever code. When we can write syntax around value semantics here, use it regardless, because the ampersand operator is a ridiculously powerful operator around readability. If all I did was show you this return, all we know is we're taking a copy of U, whatever it is, and we're copying it and passing up the call stack. That's all we know. But if I show you this, and you know nothing else about U, you do know one thing. U, whatever value it is being shared. It's being shared up the call stack. We now know that there's an allocation here. We now have complete readability. We understand the impact of this particular line of code 100%. And this is what I meant about not writing code that hides the cost. Now, everything after this will have to use pointer mechanics. But why walk away from this readability? Because doing so means you're being clever. And remember, readability is also about the average developer on our team being able to read and understand that code, bringing everybody else up, and everybody else understanding where they were at some point in their life as well. Okay, so escape analysis. Escape analysis is the only thing that can determine whether a value gets to stay on the stack, specifically the stack frame for that function, or it has to be moved to the heap. We now have an allocation. We now have garbage collection that has to be brought in. Only escape analysis can make this decision. The convention of your code will determine what happens. And by understanding escape analysis and the convention, we can make better API design choices. And later on, when we're profiling things, we'll have a better understanding of how to maybe reduce some allocations when it is practical and reasonable to do so. Now, I want to share another thing with you here. I told you that Go's stack starts out at 2K. K, not very large. You might be saying, Bill, why is that so small compared to a thread that uses a meg of memory? Again, Go puts integrity first, but it also understands that there are resources on every machine that we run that have to be shared. And it has to be shared in a reasonable and practical way as well. And so by allowing every Go routine to have just a 2K stack, we could really have a large number of Go routines, not large numbers of paths of execution that operate concurrently by still minimizing the amount of memory. And I want you to also think about something. When you look at any top-level function you've ever written, any algorithm you've ever written, I mean, how many function calls deep do you actually go? I mean, if you went like 10 function calls deep, you're probably going pretty far. And how much stack space do we really need for 10 function calls deep? We don't need a lot. And that's the other beauty here, is that this 2K stack may actually be more than enough memory that we need in the lifetime of any Go routine.